So we'll continue from where we left yesterday. Yesterday, we ended at the mean value theorems. And today, so yesterday we covered the three mean value theorems: Fermat's theorems, Rolle's theorems, and Lagrange's mean value theorem. So we'll continue further from there. Extension of Lagrange's mean value theorem, but not so often used, at least in problems at our level, is the Cauchy's theorem. Lagrange's mean value theorem is applicable for only one function. Cauchy's theorem, so let f of x and g of x be two functions which are continuous in the interval closed AB and differentiable in the interval open AB, and their derivatives do not vanish simultaneously. That means there is no common point at which both the derivatives are zero. And the denominator, this the function in the denominator, does not have equal values at the extreme ends of the interval. That is, g of a is not equal to g of b. Then there exists at least one c belonging to AB such that f of b minus f of a by g of b minus g of a is equal to f dash c by g dash c. Remember, one important point to remember is this c is the common point. It is not that the c is different for, so it is not that we have f of b minus f of a by b minus a is equal to f dash c, and then g of b minus g of a by b minus a is equal to g dash c. This is by Lagrange's mean value theorem. However, the c may be different for both the functions, but Cauchy's theorem says as long as this doesn't happen, there will be one common c where the ratio f of b minus f of a by g of b minus g of a will be f dash c by g dash c. So this is provable by Lagrange's mean value theorem. Of course, we'll not get into the proof of it, but this is the Cauchy's theorem. More important theorems for us coming up are the Taylor's theorem. There's again an extension of Lagrange's mean value theorem. So Taylor's theorem with Lagrange's form of remainder. Now, if f of x is continuous and differentiable n plus 1 times on a closed interval a comma a plus h, then for any x belonging to a comma a plus h, f of x is this. So f of x is equal to f of a plus x minus a by 1 factorial into f dash a, x minus a whole square by 2 factorial into f double dash a, so on, and x minus a whole power n by n factorial into nth derivative of a plus this remainder. So let us write this in other form. See, we talked about a plus h. So the common form in which this is written is f of a plus h is equal to f of a all right, plus h by 1 factorial into f dash a plus h square by 2 factorial into f double dash a, so on, plus h power n by n factorial into nth derivative of f at a plus h power n plus 1 by n plus 1 factorial into n plus first derivative at c, where c is a plus some theta h, where theta lies between 0 and 1. What it, see, this is, we are expanding a plus h, f of a plus h is f of a plus h by 1 factorial f dash a plus h square by 2 factorial into f double dash a, so on up to here, up to nth term plus this term. This c is a number between a and x here. So what we have done here is a plus h we have taken as x, and c is some number between a and x. So this is called as the Taylor's theorem, and this term at the end is the Lagrange's form of remainder. All right, this is the remainder term, h power n plus 1 by n plus 1 factorial into nth derivative of f at c. This is the Lagrange's form of remainder. So we can remember this Taylor series either in this form, what I just showed here, or you can remember in the form that is here typed, f of x is equal to f of a plus x minus a by 1 factorial into f dash a, x minus a the whole square by 2 factorial into f double dash a, so on, x minus a whole power n by n factorial into nth derivative of a plus x minus a whole power n plus 1 by n plus 1 factorial into n plus first derivative of f at c. Now this is called as Taylor's series expansion with Lagrangian form of remainder expanded about x equal to a. All right, this is the Taylor's theorem about x equal to a. Now you see, we can show that Lagrange's mean value theorem is just a subset of this Taylor's theorem. So if you just take the first two terms, that means these two terms, if we just take, all right, so take in this expression these two terms, what do we get if we are approximating it? So f of x is equal to f of a plus x minus a by 1 factorial into f dash a. So of course this will be, when we limit it to just two terms, then this remainder will be an approximation. So we will get c here, not a, because we are making the approximation leaving out the higher order terms. So f dash c is f of x minus f of a by x minus a. So this is Lagrange's mean value theorem. Okay. So when we stop at this, that means we have ended at the second term. So what we get is this Lagrange's mean value theorem. So Lagrange's mean value theorem is a particular case of Taylor's theorem. All right. Now, next, we can have Taylor's theorem in another form with Cauchy's form of remainder. This is little different. However, most popular is for our purposes without going too deep into these series. For our purposes, this is, we stick to Lagrange's form of remainder, but we should know the Cauchy's form of remainder. All terms remain same except for the last one. In the last one, instead of having x minus a whole power n plus 1 by n plus 1, we have a different term here. X minus a into x minus c whole power n by n factorial into f of, f of the n plus first derivative of f at c. So that's the only difference. Now, when x, Taylor's theorem expanded about x equal to a, we have seen that. Now the same thing we expand about x equal to 0 becomes Maclaurin's series. This becomes Maclaurin series, and this is a very important series for us. So Maclaurin's theorem with Lagrange's form of remainder. So f is a continuous function and differentiable n plus 1 times. Then we get f of x is equal to f of 0 plus x by 1 factorial into f dash 0 plus x square by 2 factorial into f double dash 0, so on, plus x power n by n factorial into nth derivative of f at 0, plus this last term. We replace, x power n plus 1 by n plus 1 factorial into f nth derivative at c. So not x at c, you just this at c. Now, as I've given in the earlier when we were doing limits, I showed that we have the standard Maclaurin's series. Yeah. Usually when the remainder term tends to 0 as n tends to infinity, we get what we call as the infinite Maclaurin series. So this is the infinite Maclaurin series. And these are some of the standard series, and some of them we should remember directly, which is e power x, a power x, log of 1 plus x. These are some standard ones that we must remember. Sin x and cos x. Tan x may not be. At least the first two terms we can remember, or if needed, we can derive on spot using this expansion. So this in this application of derivatives, we are showing that a function can be approximated to a polynomial. You have converted any complex function into an algebraic type of function in a series expansion. All right, where these are coefficients, f of 0, f dash 0, f double dash 0, f triple dash 0, these are all constant terms. So we get as a power. Now, to how much power you want to approximate, you can approximate. As I showed you earlier, just a second, I'll just stop the screen share for a moment. I will just open what I had shown you some time back. Yeah. Yeah, I'm sharing the screen now. Yeah. So this is the graph of sin x. We know this is the graph of sin x. Now, if I take the first term of the Maclaurin series of sin x, what is that? First term of the Maclaurin series of sin x here, x. Okay. So when I choose that, so I've chosen that, I just get a straight line, y equal to x. So this is the approximation. Now, when I choose two terms, x minus x cubed by 3 factorial. See the next. This is the approximation. Because it is just two terms. It's a cubic function. So it will have a graph like this. So close to 0 and nearby 0, sin x and this curve are matching. And away from, almost like minus pi by 2, less than minus pi by 2 and greater than pi by 2, there is a lot of difference. The two curves diverge. Now I add more terms. So here, the next series that you are seeing here, I have 1, 2, 3, 4, 5, 6 terms. So six term approximation. Now you see here, the curves match more closely. And here I have another two terms, x power 13 by 13 factorial and 15 by 15 factorial. And you see, there is more overlap. So like that, as n tends to infinity, you keep adding the terms in the Maclaurin series. This merges with the sin x curve. So there's a beautiful application of derivatives here, that you can get a function written in a power series form, and then we can use it in different ways. If we are dealing with a region close to 0, then very good. We will be able to approximate it with an algebraic function instead of a transcendental function. These functions, sin x, cos x, tan x, log x, e power x, these are called as transcendental functions, which are non-algebraic. So that is the application. So we can show that the same thing is valid for other graphs also. I'll choose cosine now. So I have shown this earlier. So there's the cosine graph. With the first term approximation, we get this not at all matching. Two terms of the Maclaurin series. This is the graph. Three terms, there's this much overlap. Four terms, not four, 5, 6 terms, a big overlap. And then adding another two terms, see the overlap. So for all functions, we can show it this way. Now, let us see the type of questions we get um, in GATE. See, this is a collection of a period of 10 years of GATE questions in different divisions: civil, mechanical, electronics, electrical, so on. And we see here, we get enough over a period of 10 years, you got enough number of questions on this, just on this topic, Taylor series expansion. So we will do some of it right now. Yeah. So okay, I'll copy this also. So the third term in the Taylor series expansion of e power x about x equal to a. So let us write the Taylor series expansion. F of x is equal to f of a plus x minus a by 1 factorial into f dash a. This is the second term. The third term is x minus a the whole square by 2 factorial into f double dash a, so on. So this is the third term that is being asked for. So f of x is e power x. So first derivative is e power x itself. The second derivative is also e power x. Therefore, second derivative at a is e power a. Therefore, the third term is x minus a the whole square by 2 factorial into e power a. Very simple question. Just direct application of the Taylor series expansion. All right. Clear?
Yes, sir.
Now, we'll do a few questions on this. Convergence and divergence I have to do after integral calculus completes, but you see here the Taylor series expansion of sin x. Very, very simple. Directly x minus x cube by 3 factorial plus x power 5 by 5 factorial, so on. That means you just have to remember the series expansions. That's it. You don't have to do it. Let's do this. This is the Taylor series expansion of sin x about x equal to pi by 6. So how many terms? Let us see. At least 4 terms we can expand. So f of x is f of a at pi by 6 we have to do. Then x minus a by 1 factorial into f dash a plus x minus a the whole square by 2 factorial into f double dash a, and so on. So f of x is sin x. What is the derivative of sin x? Cos x. What is the derivative of cos x? Minus sin x. And what is the derivative of minus sin x? It will be minus cos x. Now, so we are expanding about x equal to pi by 6. So what is f of pi by 6? Sine pi by 6. What is sine pi by 6? Half. F dash pi by 6 is cos pi by 6. Cos 30 is root 3 upon 2. Then f double dash pi by 6 is minus sine pi by 6 minus half. So up to 4 terms we can write this minus root 3 by 2. So f of x is sine x. We can write this as f of a, that is half, plus x minus pi by 6, x minus pi by 6 by 1 factorial into f dash root 3 by 2 plus x minus pi by 6 whole square by 2 factorial into this term f double dash, that is minus half, plus x minus pi by 6 the whole cube by 3 factorial into minus 3 by minus under root 3 by 2 and so on. So now we can observe which one is the right answer. So you can see here half plus root 3 by 2 into x minus pi by 6 minus 1 by 4 into x minus pi by 6 whole square minus root 3 upon 12. 3 factorial is 6 multiplied by 2 is 12. So minus root 3 upon 12 x minus pi by 6 whole cube. So this is the correct answer. Now students generally in haste can make this mistake that sine x is x minus x cube by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial and so on. So if I have to expand about x equal to pi by 6, I replace x by x minus pi by 6, x minus a. That's a mistake. That's a mistake because this is the expansion for Maclaurin series about x equal to 0. So these are derivatives, terms are derivatives at x equal to 0. Whereas in this case, the derivatives will be at pi by 6. So therefore, the expression comes out completely different. If we try to do this shortcut, we may think that this is the answer. We may think that this is the answer, but this is actually not the answer. All right. So, okay. I would want you all to do this and tell me the correct answer. One or two more problems. I have not uploaded in class time today. I'm sorry. Just a second. Yeah, please do this. Expansion of e power minus x. Acha, this is linear approximation. So for the function e power minus x, the linear approximation around x equal to 2. Please do this. Tell me what is the right answer. A, B, C, or D. You can put it in chat. Sorry. Answers. Anyone? No answers so far. Linear approximation means you will approximate only to the first power of x. So far, no answer. It's not a difficult one. Good. One answer. One answer. Attempt. Good. Two answers. Three. Four. All right. All right. Now just look at this. Now linear approximation means this. We f of x is f of 2 plus x minus 2 by 1 factorial into f dash 2. That's it. Third term we will not go for because this is a linear function. Third term will be x minus 2 the whole square. It will be a quadratic function. So now f of x is e power minus x. So what will be f dash x? Minus of e power minus x. E power minus x into minus 1. That's all. So f of 2 is e power minus 2 and f dash 2 is minus of e power minus 2. So therefore, the linear approximation is f of x is f of 2, that is e power minus 2, plus x minus 2 into minus e power minus 2. So when we take e power minus 2 common, we get 1 minus of x minus 2. So e power minus 2 into, this is 3 minus x. E power minus 2 into 3 minus x. So A is the correct option. A is the correct option. Okay. So some of you have written D, but D is a constant. It is not a linear approximation. E power minus 2 is a constant number. So
Sir, one
that
doubt.
cannot, yes.
Like if we have taken more terms, then like if x minus 2 the whole square, it will also have some linear terms, right?
Yeah, but you have not approximated it. Yeah, good question. It will have a linear term, but you have not truncated at a linear factor. You have truncated at x minus 2 the whole square factor. So it will have a linear term, but x square is also there as an approximation. No? It is already a quadratic. It is not a linear function. Understand? No? X square term will also be there. So it is already a
Linear
quadratic expression.
We should, like the highest power should be linear.
Yes.
Expansion. Okay.
Yes. Good. So we get questions of this type. This one, let's try this. This will be easier. Which of the following would have odd powers of x in Taylor series expansion? About x equal to 0. That means he's talking about Maclaurin series expansions. Which of the following, maybe more than one, can be? So sine x cube, sine x square, cos x cube, cos x square. Do you remember the series, or should I show the series? You can see this series here. Sorry. Answer. Let's see the chat. This is from the previous question. You don't have to expand. You just have to see the series and tell the answer. You don't have to do the whole expansion again. Good. 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 So this one is the correct answer. The reason is simple. Cos x is already having terms with even powers. Remember, cos x is already even function. It already has even powers. 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial. Now, within this, if you replace x by x cube, of course, the factors will change. You don't worry about the factors, but powers will not change. So x, you have to replace x by x cube. All right, and here x by x cube and x by x square, it always remains even. Only that which will have odd powers is this term, x cube. So this is a rough approximate analysis. It is not that we actually write a Taylor series. If I replace x by x cube, I get the powers of x. Coefficients will change because the derivatives will again change, and you will have different terms. So we need not go by all those things. But as far as expressions are concerned, the powers are concerned, just replace x by x cube. Okay. So this is Taylor series expansions. So now we move on to next. I will give these other questions in assignment. You can please practice. Very soon I'll be releasing the assignment. I've already started uploading. It's not yet completed. Next, very important application. Yes. Is monotonicity and maximum and minimum values, or maxima or and minima of functions. And this is by far the most important topic as far as gate is concerned, because most of the questions come, and those of you who have appeared for JE, you also know that this is one of the most important topics at any entrance level. But remember, for gate, you will have maxima and minima for multivariate functions also. Soon we'll do functions of several variables, so that will also come. Now, the monotonicity of a function. Monotonicity means same behavior. It means like we say, it is very monotonous. Monotonous means it is of the same tone, or there is no change, there's no variation. So monotonicity in functions is referring to its increasing nature or decreasing nature of functions. A function is monotonically increasing or monotonically decreasing. So we apply that for increasing nature or decreasing nature. So for example, y equal to x is a graph, we know, is a straight line like this. Y equal to x, it is a monotonically increasing function. All right, it increases. Whereas y equal to minus x is a monotonically decreasing function. Simplest of examples. Monotonically increasing function, and this is a monotonically decreasing function. Now, this has a bearing on maxima and minima. It's very important. Now, increasing and decreasing nature, very important is we move from left to right on the x-axis. When we are moving from left to right, that means we are moving towards increasing values of x on the x-axis. Then if the function value is increasing, then it is monotonically increasing. And if the function value is decreasing, then it is monotonically decreasing. It is not the other way. If you go from right to left, it shows other ways. But we are not doing that. We are going from left to right. Now, how do we define this monotonic nature? So what is an increasing function? Increasing function. Now, if for all x1 and x2 belonging to the domain of f, I'll write D, each time I'll not write domain. If for all x1 and x2 belonging to the domain of f, if, okay, for x1 less than x2 implies or double implies that f of x1 is less than f of x2, then f is said to be strictly increasing function. It is said to be strictly increasing function. That means, look at the graph. Very simple way of explaining. Now, x1 is a smaller number, x2 is a larger number. Function value at x2 is larger than function value of x1 at x1. Now, no matter what, x1 and x2 can keep changing throughout the domain. But if the function value of a greater number is greater than as compared to the lesser number, then it is an increasing function. And it is strictly increasing. Now, but if for x1 less than x2, the double implication is f of x1 is less than or equal to f of x2. That means the function values of 2 points can be equal. They can increase and then they can be equal also. For example, let's take this function. Okay, this is a function. On this region, there are function values at 2 points which are equal. Or in fact, in this whole region between x1 and x2, this is constant value. It's a now such a function, then f is said to be increasing. We don't call it strictly increasing. We say increasing or non-decreasing. Okay. Now, this is the fundamental definition. Now, we'll use this in derivatives. So in derivatives, f dash x is limit h tending to 0, f of x plus h minus f of x upon h. H is a positive quantity. Now, if x plus h is greater than f of x plus h is greater than f of x, it means it is an increasing function. For suppose this is an increasing function, x plus h is greater than x. So f of x plus h will be greater than f of x. So it is limit h tending to 0, a positive value by a positive value. So the derivative will be greater than 0. The derivative will be greater than 0. So definition using derivative. So definition using derivative. Okay, yeah. A function is said to be continuous. Just a second. So if a function is continuous and differentiable in its domain and f dash x is greater than or equal to 0 for all x belonging to the domain, and f dash x equal to 0 only at isolated points, then f is said to be strictly increasing. So we have seen here that f dash x greater than 0 means it's an increasing function, the slope. Now, sometimes it so happens that at some isolated points, f dash x can be equal to 0. So, for example, y equal to x cube. Let us take this example. This is a very important example to understand monotonicity. So here we see, so this is the function f of x equal to x cube. The derivative is 3x square, and the derivative becomes 0 only at x equal to 0 and nowhere else. So at x equal to 0, you get a horizontal tangent. But for all other x, the derivative is always positive. So this equal to 0 is only at one point, an isolated point. It is not over an interval. The previous graph that I showed here, this one, the function is function value, the derivative is 0 over this interval because you have a horizontal line. Over the entire interval, it is 0. So this is not strictly increasing, whereas this is a strictly increasing function. So we should not get under the impression, of course, f dash x greater than 0 throughout, it is a strictly increasing function. But f dash x greater than or equal to 0 is also strictly increasing as long as f dash x is 0 only at isolated points. This is an example for it. So based on this, now decreasing function, we can similarly write for decreasing function. For decreasing function, so if for all x1 comma x2 belonging to the domain x1 less than x2 implies or double implies f of x1 is greater than f of x2, then function is strictly decreasing. function is strictly decreasing. So what we get, f of x1 is greater than f of x2. So function is a decreasing function. All right. Now, it need not be strictly decreasing. We can get a case like this where, the function is like this, constant in between, and again like this. Then it may not be strictly decreasing. But however, in using derivatives, when we define again, please go through these notes. I've already shared with you. What I'm doing in class is based on what I'm discussing here, you review, you will understand. So if f dash x is less than 0, then it's a strictly decreasing function. So just take this minus x cube, the graph changes. So this is the graph. So there's a strictly decreasing function. So at any given point, you see the tangent will have a negative inclination throughout. At only at one point, at x equal to 0, the derivative will be 0. But all other points, the tangents will have negative slope. So function is decreasing. That means when we are moving from left to right across x-axis, the value of the function is decreasing. Okay. In this case, when we move from left to right, the value of the function is increasing. Now, a function can be increasing for a while and decreasing for a while. Isn't it? Our graphs of sin x and cos x are like that. Now, these are not, you cannot say they are strictly increasing functions or decreasing functions. These are increasing on a certain interval and decreasing on a certain interval. Okay. So sin x, the graph of sin x, it's an increasing function on, you see, minus pi by 2 to pi by 2, it increases. In this region, it increases. And then pi by 2 to 3 pi by 2, it decreases. So 2k pi minus pi by 2 to 2k pi plus pi by 2. Sin x is increasing for every periodic, its periodicity. Period is 2 pi. So you keep adding 2 pi. For every that interval, the sin x will be increasing, and it is decreasing for, or we should say decreasing, okay, decreasing for the interval 2k pi plus pi by 2 and 2k pi plus 3 pi by 2. So these functions, we say they are monotonically increasing in a particular specified interval only. It is not throughout. Okay. So this is about monotonicity. And this is very useful in graphing. When we do curve tracing, this is something extremely important. Now next. How about the second derivative? Now, this is something very important. This is of great use to us in curve tracing. A function may be increasing or decreasing, but its curvature, you see the curvature, this is, concave up. It is concave portion is upwards. Here there is no curvature, it's a straight line. And here there's a curvature which is concave is down, or the convex portion is up. So what makes the difference? So here you see f of x1 and f of x2. F of x2 is greater than f of x1, where x2 is greater than x1. Now, because we can see the function is increasing, so when you move from left to right, the first derivative is 0. The first derivative is 0. Now look very carefully. At x1, I draw a tangent. At x1, I draw a tangent, and at x2 also I am drawing a tangent. Whose slope is greater? The tangent at x2. The inclination is greater with the x-axis, so the slope will be greater. What is slope? Slope is the derivative. So f dash x gives us the slope. So now what is happening is, now when you study these slopes, when you move from left to right on the x-axis, the slope value for this function is increasing as we move from left to right. So in this case, f dash x is an increasing function. In the first case I'm talking about. So if f dash x is increasing function, then its derivative must be greater than 0. So you get that the second derivative is greater than 0. So when we get second derivative greater than 0, we get a curvature in the curve which is such that the concave portion faces upward. Just like first derivative means it tells about the tangent, it has positive slope. So just by seeing this curve, we can say, okay, this is, increasing function. The first derivative is positive. At any point you take, the first derivative is positive, right? Similarly, if you have a curvature with concave facing upwards, it means that the second derivative is positive. Whereas now look here, this is an increasing function, but f dash x is a constant. F dash x is positive, but is a constant here because there's a line, f of x is a straight line. So first derivative will be a constant. All right, it is of a constant slope. So second derivative will be 0. So when second derivative is 0 means the curve will not have a curvature, at least at that point. But here throughout second derivative is 0 throughout. So it's a straight line. Understood? And here this is an increasing function. We can see if I draw a tangent here, at x1 I'm drawing a tangent. This is the tangent, and x2, I'm drawing a tangent. Now the slope of the tangent at x1 is higher than the slope of the tangent at x2. So as I'm moving from left to right, my slopes f dash values are decreasing. So in this particular case here now, for this case, f dash x is a decreasing function. This is a decreasing function. So what we get here is f double dash x will be negative. All right. F dash x will be negative. Now, same concept, let us look for decreasing functions. Decreasing functions, it is very clear. Function is decreasing. At every point, f dash x will be negative, negative, negative. No problem. We know that. You see the tangent here. It's having a negative slope, negative slope, negative slope, negative slope. Okay. So tangents have a negative slope. So this is a decreasing function. As we move from left to right on x-axis, the function is decreasing. So first derivative will be negative. But then you see here, okay, this inclination is closer to y-axis and it is a negative inclination. All right. And this inclination, this line, tangent line is, more inclined towards the x-axis. So what will be the value? This will be close to, say, minus infinity, and this will be a negative value but close to 0. So the values of the slope are changing from some large negative number. I should not say large negative number, numerically large, but with a negative number. So it is a small number. Minus 100 is much smaller than minus 1. All right. So the slope is changing from a numerically large negative value to a numerically small negative value. So actually the values are increasing. So f dash x is an increasing function. Therefore, f double dash x will be positive. In this case, f dash x is negative and its slope will be equal throughout, and therefore the second derivative, because f dash x is a constant, the second derivative will be 0. And here in this case, we see the slope is a number close to 0, and this is close to minus infinity. So when you move from left to right, the values are changing from, say, minus 2, minus 3, minus 5, minus 10, minus 100, so on. So the values are decreasing. So f double dash x, so f dash x is a decreasing function. So f double dash x will be negative. So this is the conceptual understanding of why second derivative is greater than 0 or less than 0. But now, notwithstanding all this, so in both the cases, what we get is this. In both the cases, what we get is, if second derivative is positive, it means the curve is concave upward in curvature. So while tracing the curves, this is very important. How will the graph be? Will it be positive upwards? Will it concave upwards or concave down? downwards we have to see. So whether it is increasing or decreasing, as long as the second derivative is positive, it is concave up. Whether it is increasing or decreasing, as long as the second derivative is 0, it's a straight line, increasing or decreasing. And whether it is increasing function or decreasing function, if second derivative is negative, concave portion is facing downwards and convex portion is facing upwards. This is the nature of curvatures. This will be extremely useful in curve tracing. All right, we will discuss this again just before finding the areas and the curves, but this is a very important part of monotonicity and finding monotonic functions and its use in finding maxima and minima. Now next is our target is to find maximum and minimum. So for that, once we have studied monotonicity, now we study what is called as the critical points in the domain. Critical points, we examine critical points because we want to find out at the critical points whether the function reaches its maximum or not. All right. So which are the critical points that we need to examine for maxima and minima? Points where f of x is defined, but the points where the derivative is 0 or undefined, these are called as critical points. So graphically, the critical points are points of discontinuity, points of horizontal or vertical tangent, and points of sharp corners. Right, points of sharp corners where tangent is not unique. That means the function is not differentiable. So when we check the graph of a function, these are some of the critical points. For example, this is a function. Now, these are the points. Now we want critical points. The points where the first derivative is 0. These are critical points. Point where there is a sharp corner. There we have to check whether the function is maximum or minimum. And the point where there is discontinuity. This also, so these are the critical points. C1, I'll change the color. Critical point 1, critical point 2, critical point 3, critical point 4. Like this. So these are the critical points. To ascertain whether the function has reached maximum or not, this is maximum or minimum value we have to see. And maxima and minima is by far the most important concept in functions, because in engineering and otherwise also, not just in engineering, in economics and medical science, wherever we study data, and data has continuous data forms curves, and we see what is the peak point, what is the low point, so on. All right, so we study the maximum and minimum. One more critical point a very important critical point is the point of inflection. Before we move on to maxima minima, understanding of point of inflection is a very important concept. Okay. So for a twice differentiable function, y equal to f of x, if the second derivative is 0 or undefined, but the first derivative exists, then such points are called as the points of inflection. Second derivative is 0 or infinity, undefined. First derivative exists, then it is called as the point of inflection. More importantly, you see here, this will be much easier to understand. A point of inflection is a point at which the curve changes its curvature from concave up to concave down or vice versa. That means at these points, the second derivative will be 0 and the second derivative changes sign from negative to positive or positive to negative. Let us study this. Then we'll understand the point of inflection. Y is equal to x cubed. This we have just now studied that this is a strictly increasing function. So we just studied that this is a strictly increasing function. So here f of x is 3x square, f dash x, sorry, f of x is x cubed, I'm sorry. F dash x is 3x square, f double dash x is 6x. Now at x equal to 0, f dash x is 0. All right, here f dash x is 0. Now for x less than 0, f double dash x is negative. F double dash x is negative, and for x greater than 0, f double dash x is positive. So you see here, this portion f double dash x is greater than 0. For this portion, f double dash x is less than 0. And at this point, f double dash x is equal to 0. So this point is called as the point of inflection. Now you see the curvature here, it is convex upwards. And here it is concave upwards. All right. So at the point of inflection, this is very important. The curve changes its curvature from convex to concave or vice versa. All right. Then it is a point of inflection. So interestingly here, you have the first derivative as 0. But you will not find that this is a maximum point or minimum point. All right. What did Fermat's theorem say? That if the point is an extremum, you will get f dash x is 0. But converse is not true. F dash x is 0, but point may not be a minimum point or a maximum point, because it's a point of inflection. Another way I tell the students to remember point of inflection, okay, is this. You can remember this way of presenting it. It removes all confusions. At the point of inflection, the curve crosses its own tangent. Now, usually the concept of tangent is like this, that this is, sorry, this is a line. And the curve may be a circle or an arc or a parabola or whatever. The curve usually, approaches the tangent and moves away from the tangent. That's what a tangent is. So very layman definition in high school, we say that tangent is a line that touches the curve at one point. That is not a accurate mathematical definition, but at that time, to give a conception of tangent, it was good enough. But it is not a mathematically accurate definition, because here you see f dash x equal to 0, the slope at x equal to 0 is 0. So the tangent is the x-axis. And here we see that the curve reaches the tangent and crosses over the tangent. It reaches the tangent and crosses over the tangent. So this is the point of inflection. And we get the points of inflection for other graphs. Okay, sin x or cos x. We'll take sin x. Okay, sin x graph. Okay, I'll plot it in. Here, advantages, I get many points. I'll take. So this is the graph of sin x. Now I will identify points of inflection here. Y equal to sin x. Now these are points pi, 2 pi, 3 pi, 4 pi, 5 pi. N pi is what? 0 is there, minus pi, minus 2 pi, so on. Okay, now at these points, if you see the tangent, if you draw a tangent line, this will be the tangent. The curve crosses over its tangent. And you can see at all these points, you can see the, so these are points of inflection for sin x. These are points of inflection. What is derivative of sin x? Cos x. What is the second derivative of sin x? Minus sin x. So between this, I'll write it as f. So between 0 and pi, the second derivative is negative. Between pi and 2 pi, the second derivative will be positive. Because sine value is negative, so minus of sine will be positive. And here again, the second derivative is negative. The second derivative is positive. So you see, this is convex, concave, convex, concave, so on. So these are the points of inflection. At these points, pi, 2 pi, 3 pi, the second derivative is 0. And across these points, the second derivative is changing the sign from negative to positive, from positive to negative, negative to positive, so on. So these are called as the points of inflection. So sometimes the points of inflection may have the first derivative as 0 here, but because they are point of inflection, you will not get a maximum or minimum. All right, is this clear? Is this section clear? Today's class is an extremely important class. You should go and check back this video again. I have covered things of great depth conceptually. You should go through these concepts again, because if you understand the concepts many times, just visually you can solve the problem without using a lot of pen work. That's why these concepts are important. And of course, mathematically, we should understand this. These are very important ones. Next, coming to maxima and minima. Okay, there are 3 definitions. Let us do one by one. First is an algebraic definition. Before I begin, I should explain some things. So let's say we have a function. Let's say we have a graph of a function like this. Okay. Now, this is the end of the interval, the ends of the interval. The leftmost point is A, rightmost point is B. Now, this graph shows that there are many points which has peaks here. All right. Now, in the very vicinity of this point, so let us say we say critical points. These are critical points: C1, C2, C3, C4, C5. Okay. Now, locally, just in the neighborhood of C1 and in the neighborhood of C3, in the neighborhood of C4, these points are maximum there. So in the neighborhood of C1, f of C1 is the largest value. So we call this as the local maximum. Local maximum values. These are local maximum values. Now, local maximum, and then similarly, these values here. Oh, I missed one point here. Okay. I'll just mark this point as C. Now, these points are local minimum values. This one, and this one. These are local minimum values. But amongst the local maximums, one value will be greatest throughout the interval that we are considering, A and B. So for the interval AB, the largest of the maximum values, this will be called as the global maximum. This is called as the global maximum. And of the least values, of the local minimum values, whichever is the lowest, all right, this one is the global minimum. So this concept we need to be clear. So this is the terminology we will use. So depends on what is being asked. So let's see the algebraic definition, then using first derivatives and then using second derivatives. All right. A function f of x is said to have a maximum at x equal to a if f of a is the greatest value in a suitably small neighborhood of a, where x equal to a is an interior point in the domain of f of x. So very simple. It doesn't talk about derivatives here at all. What it says is f is said to have a maximum at x equal to a if f of a is the greatest of all values in the neighborhood of a. So we write this as f of a is greater than or equal to f of a plus h, and f of a is greater than or equal to f of a minus h, where h is a small value. This way of definition will take into account non-differentiable functions also. This is the fundamental definition. In fact, more of a functional definition. Even if we don't have a derivative, function is not differentiable or function is discontinuous, still this fundamental definition is always valid. So for discontinuous functions, we have to look into this definition. This is a, and this is a minus h, and this is a plus h, and we can keep changing the values of h. H is a very small positive quantity. So this is f of a is greater than f of a plus h, all right, and f of a is greater than f of a minus h. So f of a value on the y-axis is larger than f of a plus h and a minus h and a plus h. So f of a values graphically is lying above a plus h and a minus h. So this is called as the local maximum. And for minimum, the same thing applies here. So let's say this is the least value a. Now we have a plus h and a minus h. So this is f of a, its value is lower than f of a plus h, and its value is lower than f of a minus h. Okay. Oh, here, I'm sorry, it is b. I didn't see this. So for x equal to b, so I'll change this to b. B, b plus h, b minus h. So we have, this is b minus h, f of b plus h. So these values are lower. F of b is this value, and this is f of b minus h is greater than f of b. F of b plus h is also greater than f of b. So this inequalities hold. F of b is less than f of b plus h and f of b is less than f of b minus h. In that case, this function is the local minimum. Now, when we look at this from derivative point of view, the first derivative test is also a very important method. Generally, we think of it as a second derivative test, but first derivative test sometimes is much faster than the second derivative test. So first derivative test is, I am just going to base my conclusion of maximum and minimum based on the first derivative. So this is the first derivative test for maximum. At a critical point, x equal to x naught, where f dash x naught is equal to 0. That means at this point, there is a horizontal tangent. Now, if f of x changes sign from positive to negative while moving from left to right across x naught, then f has a local maximum value. All right, I'm sorry, this is not f of x, this is f dash x. F dash x changes sign from positive to negative while moving across from left to right. Then f of x has a local maximum value. If f dash x changes sign from negative to positive at x equal to 0 while moving from left to right, then f of x has local minimum value. And f dash x does not change sign at x equal to 0, then f has neither maximum nor minimum value at x equal to 0. Let's examine these three cases. Okay, I'll draw. So here, let's see a local maximum. So here at this point, the derivative is 0. Derivative is 0 means you will get a horizontal tangent. So this is this point x naught, and we are getting f dash of x naught is equal to 0. But before that, here f dash, sorry, here f dash and f dash here, f dash has positive value because the function is increasing, and here it has negative value because the function is decreasing. You take tangents at any point here. So the function is increasing, reaching a maximum point, and then decreasing. So f dash x is changing from positive to negative. When we move from left to right across x naught, f dash x values changes from positive to negative, and f dash x naught is 0. Then this is the point of local maximum. So locally, it is a maximum value based on derivatives. Of course, for this, the function has to be a continuous and differentiable function. Now, let us look at the local minimum. X naught. This is the horizontal tangent. F dash of x naught is equal to 0. And here, f dash is positive. Towards the left, f dash is negative. So what's happening? So here the function is decreasing. F dash x is less than 0. Then it reaches the minimum point and then function increases. So across this, the derivative values is changing from values from negative to positive. When we move across x equal to x naught, the first derivative value is changing from negative to positive. And at x naught, the first derivative value is 0. Then this is the point of local minimum. This is the point of local minimum. What is the point of local minimum? X naught. So x equal to x naught is the point of local maximum here. And f of x naught is called the local maximum value. So remember, x is called as the point of minimum or point of maximum, and f of x naught is called as the point of the maximum value or the minimum value. Okay, don't, here it is point of local minimum, and f of x naught is the local minimum value. Okay, now comes an interesting case where it doesn't change sign. Like for example, we f dash x is 0, but it doesn't change sign, like we had the case of y equal to x cube. All right, previously we did that, but a similar case here. So at this point, now f dash x naught is 0. However, f dash x is positive before x equal to x naught, and f dash x is positive after x equal to x naught. That means for x greater than x naught and x less than x naught, f dash x doesn't change sign. It remains positive and positive, although f dash x is equal to 0. That is this case. F dash x does not change sign. Then f has neither a maximum nor a minimum at x equal to 0. So in fact, if this happens, this is the point of inflection. It doesn't have either a maximum or a minimum, even when the derivative is 0. Is this clear? So this is based on the first derivative test only. And sometimes it usually is very useful to just do the first derivative test instead of doing multi-derivative test, second derivative test, for some cases where the second derivative expression itself is very, very difficult to find. We will do such problems in the next class, but this is the concept. Now next is the second and higher derivative test. So by the way, I have to cover this part. Now in an interval, okay. Achha, when the derivative test, suppose there is f dash x never becomes 0, then what? Of course, it is not just a local maximum or local minimum, it can be in the interval. So in an interval, at the extreme points of the interval AB, if f dash x is 0, f dash x is negative for all x greater than a, that means it's a decreasing function. It's from a to b, it is decreasing. Then f of a will be the maximum value and f of b will be the minimum value. So f of x has a local maximum at x equal to a and local minimum at x equal to b. This is easy to understand. And if it's an increasing function, then it will have a minimum value at x equal to a and maximum value at x equal to b. Okay, that is in the interval. Now at a point, how do you find the maxima and minima based on the second derivative test or higher derivative test? So first find the roots of f dash x equal to 0. That means find all the critical points. Now suppose x equal to a is one of the roots. Now find the value of f double dash a. Now if f double dash a is negative, then f of x is maximum at x equal to a. And f double dash a is positive, then f of x is minimum at x equal to a. Now just now I spent a lot of time explaining the convex and concave nature of the curves. Second derivative is positive, means it is a curve at that particular point has concavity facing upwards. And second derivative negative means concave portion is facing down. So now look at the same examples, the examples that I'm these three examples that I'm showing. Now from the second derivative test point of view, we will write this. So for maximum, this is the curve. Now for minimum and the point of inflection. Now let us see this. Now here clearly at x naught, f dash x naught is 0 because you get a horizontal tangent, the slope 0. And f double dash x naught will be negative. Why? Because it is a convex curvature. At this point, the convex portion is facing upward. So when there is a maximum, convex portion will face upwards. Concave portion will face, the concave side will be facing downwards. Convex side will be facing upwards. So this is local maximum. So generally people remember this as a mug up like a formula. F dash x equal to 0 and f double dash x negative, then it is maximum. But if you understand that f double dash x negative represents a convex curvature, immediately you can say that's the point of maximum. Visually, just a mental picture you can get. All right. Then local minimum here. F dash x equal to 0. At x equal to 0, f dash x is equal to 0. But f double dash x is positive. because concave portion is facing upward. So it is local minimum. And in the third case, f dash x is equal to 0 at x naught and f double dash x is also equal to 0 at x naught. So most likely it's a point of inflection, but you will have to test it. Of course, if you do the first derivative test, then you can immediately say it's a point of inflection. If you have to go by higher derivative test, then this is not, you will have to check it. So let us go and study this, what this says, this definition says. So let us say at x equal to 0, at x equal to a, f dash x is 0. Now find f double dash a. F double dash a is negative. That means f of x is maximum at x equal to a. If f double dash a is positive, then f of x is minimum at x equal to a. But if f double dash a is 0, now you cannot conclude. Find f triple dash x. Okay, and if f triple dash x is not equal to 0, then f has neither maximum nor minimum at x equal to a. It's a point of inflection. This is the higher test. But if f third derivative is 0, then third derivative is like the first derivative. If third derivative is 0, then go to fourth derivative. Now if fourth derivative is negative, then f is maximum at x equal to a. If fourth derivative is positive, then f is minimum at x equal to a. So odd derivative should be 0 and the next even derivative should have either positive or negative sign. So you can keep going on like this to check the derivative test, higher derivative test. But it is not required for us. We can at most stop at the second derivative test. If second derivative test we get this kind of a situation, go back to the first derivative test. It is easier to solve the problem from there. Okay. So this was about finding the local maximums. So today's class, it was more conceptual based. I didn't do many problems, but for the next weekend, I want all of you to review this and come, because when I do problems, we'll directly start applying concepts, either the first derivative test or the second derivative test to do it. All right. Do you have any questions based on whatever I've taught so far?
Sir, actually, I have one question. So, when we were speaking about, when you were speaking about global maximum and global minimum,
Yes.
over there, isn't it possible that f of b is greater than global maximum?
Yes, I didn't cover that, but it is possible. It is perfectly possible. F of a can be the least value, that is possible, or f of a can be the greatest value, that is also possible. So we have to take into account the boundaries also. Okay, this was just to introduce you the concept of what is local minimum and global minimum, local maximum and global maximum. Of course, I didn't give a formal definition. The formal definition we'll get in the, I'll be discussing in the next class. For an open interval, what is the method to find? For a closed interval, what is the method to find? Global minimum and global maximum. Okay?
Okay, sir. Yeah, that was it.
Any other question? All right.